What are antiderivatives, or what we also call as indefinite integrals? Now here we're starting off with a small example in order to be able to visualize better the concept. Now, for example, if I'm starting with the function x squared, and I wish to find the derivative of x squared. Now, if I were to find the derivative of x squared, I would end up with 2x. Now, 2x is the derivative of x squared according to the power rule of derivatives. However, if I were to go back from 2x to x squared, I would, in fact, be finding the antiderivative of 2x. Or in fact, an antiderivative of x squared. So x squared is an antiderivative of 2x because 2x is the derivative of x squared. However, x squared plus k, where k is a constant, if we add a constant to x squared plus that constant, if you would find the derivative to that function, the derivative to that function would still be 2x because the derivative of a constant is in fact 0. So x squared plus k, or x squared plus any constant, would still in fact be an antiderivative of 2x. So consequently, a function has an infinite number of antiderivatives or indefinite integrals that they all differ by a constant, because whatever the value of the constant is, when you find the derivative to x squared plus k, you would always end up with 2x. So we cannot really know what was the constant that we had before we find the derivative, before we found the derivative. So that is why that constant is just represented by a k, an unknown constant, just to take into account that a constant was there. So in fact, over here, whenever you're considering y equals to x squared plus k as an antiderivative of 2x, you'd in fact be ending up with a family of curves. They would all be antiderivatives of 2x. For example, here for k equals to 0, if you look at the purple curve here, this is for k equals to 0. This is y equals to x squared. Y equals to x squared is one of them. However, the one next to it, for k equals to 1, we would have y equals to x squared plus 1, and etc. Okay, so whatever the value of k is, k could be any real number, and there are infinite number of real numbers that k could take. So for that reason, the number of antiderivatives specific to one function are infinite. They represent a family of infinite number of curves where each would be represented, or each would be corresponding to a specific value of k. So the difference between two antiderivatives of the same constant is 0. For example, if I were to subtract x squared plus 1 from x squared, that difference is a constant. However, since x squared plus k is an antiderivative of 2x, now this is how we would in fact denote it. So this is the integral notation. It looks like that thin s, which could also be called the sum of the function. So over here, the integral of 2x, which is the function that we are integrating, times dx is equals to x squared plus k. So this notation would refer to the antiderivative of 2x, and over here the times dx, what we multiply the function by, this is called the differential of the function, to represent that we're finding the antiderivative of 2x with respect to the variable x. So with respect to x, so for example, if my function had a 2xy, if it had two variables, by looking at the differential and seeing the differential in terms of x, then we'd know that we are integrating here with respect to the variable x. So any other variable or parameter present in the function, you deal with them as constants when integrating. So to summarize what we've just discussed, if capital F is defined and differentiable over its domain, if f is an antiderivative of small f, that is if and only if the derivative of capital F prime is equals to small f of x. So over here, that would be denoted by, as we've already discussed, that the integral of f of x with respect to the variable x is equals to capital F of x plus k. So over here, capital F of x would in fact be the antiderivative of small f, of the function inside the integral. Now, if we were to set up our table of indefinite integral, if you were to look here for a second, if we go back for just a moment to this theorem or this property. Now, over here, you can point out antiderivatives using this property if you had both functions. For example, if you had f of x to be, let's just start with capital F of x. So if you had, if you were given capital F of x to be equals to 3x squared plus 5x minus 1, and if you were given small f of x equals to 6x plus 1, and given the two functions, you need to determine if one of them is the derivative or an antiderivative of the second one. Now, over here, of course, capital F of x having the higher degree, if an antiderivative, if one of them is an antiderivative of the other one, in that case, capital F of x has to be the antiderivative because it has a higher degree. So over here, in order to check if capital F is an antiderivative of small f, all you have to do is just find the derivative of capital F. Now, you could integrate small f using the rules that we're about to find, but if you have both functions, it is easier to use this property. So over here, if by finding the derivative of capital F, now the derivative of 3x squared, now we just leave 3 aside, derivative of x squared is 2x, and 5x minus 1 being linear, the derivative is just the slope. So that would be 6x plus 5. Now, you'd notice I'm given the other function as 6x plus 1, so that is different than small f of x. So I would deduce that capital F is not an antiderivative of small f. However, this is if you were given both functions. So if you're given both functions, you can just differentiate what you suspect to be an antiderivative in order to check if it's equal to the other function or not. If it's equal to it, if the derivative is equal to the other function, it means that capital F is an antiderivative of that function. If the derivative of capital F is not equals to the other function, in that case, capital F would not be an antiderivative of small f. However, you're not always given two functions, and in the majority of the cases, you're not given both functions. So for that reason, we need a table of indefinite integrals, and the table of indefinite integrals would actually give you the rules for integration. The same way you have rules for derivatives, you also need rules for integration. So over here, we're going to deduce or set up these rules using the derivative rules. Now, we already saw in the lesson on derivatives that the derivative of a linear expression or a polynomial of degree 1 would in fact be the slope of that linear expression. So the derivative of ax is just a, the coefficient of x. Since the antiderivative or the process of integrating is in fact the opposite of the process of differentiating or finding the derivative. So in that case, if a is the derivative of ax, then ax is an antiderivative of a. So over here, this is why the integral of a times dx is equals to ax plus k, of course, because over here I could be finding the derivative of ax plus any constant, and the derivative of a constant is 0. So in that case, I would end up with just a as a derivative for all of them. So over here, the integral, this is our first rule. So whenever you integrate a constant, the antiderivative would be a times x, the constant times x, plus, of course, the constant of integration. Now, regarding the power rule, now we know that the derivative, the power rule of derivatives would in fact consist of dropping the exponents, then subtracting 1 from the exponent. So n plus 1 minus 1 would in fact give you n. So if I wanted to integrate x to the n, what I need to do here is isolate x to the n. So 1 over n plus 1 times x to the n plus 1, its derivative would be equals to x to the n. So what I did is just isolate x to the n. So if x to the n is the derivative of x to the n plus 1 over n plus 1, then an antiderivative of x to the n would be x to the n plus 1 over n plus 1. So this is where the power rule of antiderivatives come from. And similarly for the others. Over here, since 1 over x, the derivative of 1 over x, we know it's negative 1 over x squared, then an antiderivative of 1 over x squared, since I want to integrate 1 over x squared, what I would do is isolate it. So 1 over x squared is the derivative of negative 1 over x. So consequently, the integral of 1 over x squared times dx would in fact be negative 1 over x. So these rules are really important to remember here. And similarly for the antiderivative of 1 over square root of x. So if I wanted to integrate 1 over square root of x, now which derivative rule do we know that involves 1 over square root of x? It's in fact this one, the derivative of square root of x. So over here, since the derivative of square root of x is 1 over 2 square root x, and my aim is to integrate this one, then what I would do is solve for it. Solve for 1 over square root x, which by cross multiplying the 2 would give me that 1 over square root x is the derivative of 2 square root x. So over here, this is where this rule comes from. Since 1 over square root x is the derivative of 2 square root of x, then an antiderivative of 1 over square root of x would be 2 square root of x, of course, plus k, the constant of integration. Now over here, we need to set up the rules for antiderivatives of square root of x and 1 over x to the n. So over here, in order to do that, I need to start by writing square root of x as x to the half. So this is in fact a power of x, even though the exponent is rational, but I could still be applying the power rule for n equals to half. So according to the power rule, let me rewrite it here in order to see it better. So the integral of x to the n is in fact 1 over n plus 1 times x to the n plus 1 plus k. So whenever you're finding the derivative of a power, the exponent is decreased by 1, while when you're integrating the power, the exponent is increased by 1. And similarly, when you're finding the derivative of a power, you multiply by the original exponent, while when you find the integral of a power, you divide by the new exponent. So you'd notice it's all reversed. And that is the concept of integrating, which is reversing the derivative. So over here, applying the power rule for n equals to half. So that would give me 1 over 1 plus half times x to the 1 over 1 plus half, sorry, x to the 1 plus half, of course, plus k, the constant of integration. So 1 plus half is 3 over 2. So we would have 1 over 3 over 2, which is the reciprocal of 3 over 2, which is 2/3, times x to the 3 over 2 plus k. Now over here, since the denominator of the fraction at the exponent is 2, it means that that's a square root. Now the denominator of the fractional exponent would indicate the index of the roots. So over here, that would be 2/3 square root of x cubed plus k, and we do know that x cubed is in fact x squared times x, so we could simplify this into 2/3 x square root of x plus k, which is the rule that you can actually find here. Similarly, we're going to set up the rule of 1 over x to the n, again using the power rule. So over here, the integral of 1 over x to the n can be written as a power of x as x to the negative n times dx. So replacing n in the power rule by negative n would in fact give me 1 over negative n plus 1 times x to the negative n plus 1 plus k. Now let's just simplify this into the form that we have here. So here keep in mind that negative n plus 1, whether at the denominator or at the exponent, is in fact negative into n minus 1. So over here, this negative would actually go out to the numerator, which leaves me with negative 1 over n minus 1. And that being written as x to the negative into n minus 1. Now a negative exponent, we just drop it down to the denominator for it to become positive. So over here, let me just rewrite that. So that would be negative 1 over n minus 1 x to the n minus 1 plus k. So whenever you are integrating functions in the form 1 over x to the n, you could either use this rule here immediately that we just justified. Just in case you're not seeing it, this is the negative. I've put it here outside the fraction, just in case you're wondering why this is a 1 and this is a negative 1 here. So you can either use this rule, or you could still use the power rule by writing it as a power of x with a negative exponent. It would basically be the same thing. So over here, before we do an example, let us just discuss some integral properties. So the derivative, now this is the derivative here of the integral. So the derivative of an integral would in fact bring you back to the function inside, because we know that when we integrate, we end up with an antiderivative of the function, and the derivative of an antiderivative is the function itself. Now, the integral is linear with respect to sum and difference as well, so that would work with the difference. So in case you're integrating the sum of two functions or the difference of two functions, then you could split these two integrals. It's as if this property tells you that you are allowed to integrate each term alone. Now the third property here, now if a is a constant, if you are integrating a function times a constant, now this being a constant, you can in fact put it outside of the integral. So the integral of f of x would in fact be multiplied by a. It's similar to finding the derivative of a function multiplying a constant. So if, for example, you're differentiating 3x squared, you just keep the 3 aside, and then you'd find the derivative of x squared, then you multiply that derivative by 3. It's the same thing for integrals. Okay, you can bring the constants out, but you cannot take outside of the integral a variable quantity, only constants that are multiplying the entire function. And this quick remark here says that the integral of a product is not the product of the two integrals. Similarly, for derivatives, we have seen in the previous lesson that the derivative of u times v is u prime v times v prime u, which in fact is not u prime times v prime. So do not make the mistake of finding the derivative of each term in the product. So it's similar to integrals. So the integral of a product is not the product of integrals. Now there are several techniques to find the integral of a product of two functions, where one of them would in fact be a technique of integrating by parts, which is a consequence of the product rule of derivatives, but that we will be tackling in another lesson. However, over here I have a couple of examples before I wrap up this introduction to antiderivatives. So over here we need to find the antiderivative of the following function passing through the point 0, 1. Now, if you go back to what we've discussed first, we said that if we go back here just a second, we've discussed that whenever you're integrating a function, you'd actually be finding a family of curves. And each curve in this family of curves corresponds to a value of the constant of integration, which here we represent by a plus k because we don't know what it is. However, if we are given a particular point of the function, for example, in the example we were just looking at, it says find the antiderivative that passes through the point 0, 1. So given a function given a family of functions that all differ by a constant, then I'd need to be looking here for the one that passes through the point 0, 1. So what we would in fact be looking for here is the value of the constant that would give me the antiderivative that is passing through that specific point. So going back to our example here, before I get to the point where I need to find k, I need to find the antiderivative first. So an integral of f of x dx would be the integral of the function that we have here. And please make sure not to forget the times dx, the differential of the function. So writing it as the integral of f of x equal, now mathematically that is wrong because you'd have to specify the first the variable you're integrating with respect to, plus if we've seen in the previous lesson on derivatives that the derivative f prime could also be denoted as a dy over dx. So dy over dx is in fact f prime. So cross multiplying, dy would be f prime times dx. So this is in fact what we're doing here is integrating each side. So the integral of the dy is the y, and we end up with the integral of f prime of x times dx on the right hand side. So this is why not writing down the dx is wrong mathematically. Okay, so let me just erase these. So going back to the example here, we had a square. Now over here, since this is an exponent of 2, then it is in fact practical to expand. So we would have the integral of 1 minus 2 over x squared plus 1 over x to the 4 dx. What I did in fact here use the identity a minus b all squared equals to a squared minus 2ab plus b squared. That is the identity I've used here. So now we can integrate term by term because we've seen that the product of, the integral of a sum is the sum of the integrals, so we can just integrate term by term. Now over here we've seen that the integral of a constant, according to the table of integrals or the integral rules, the integral of the constant is that constant times x because the derivative of x is 1. Now over here, minus 2 times. So this can be seen as negative 2 times 1 over x squared. And according to our table of integrals, an antiderivative of 1 over x squared is in fact negative 1 over x. Or you could be applying this property, which states that 1 over x to the n dx is negative 1 over n minus 1 x to the n minus 1 plus k. So over here, applying this property for n equals to 2 would give me a negative 1 over x. Similarly, this is this property for n equals to 4. So that would be negative 1 over 3x cubed plus k. And simplifying, that would be x plus 2 over x minus 1 over 3x cubed plus k. So if I were to call capital F of x the antiderivative we're looking for here. So now that I have found my antiderivative, now I need to apply my initial condition, or the point or the particular point I have on the curve, in order to determine the constant. Now if you're not given in particular point, you would just leave your antiderivative in terms of the constant of integration k. So, however, over here, knowing that this curve passes through the point 0, 1, it means that capital F of 0 is 1. So here, replacing x by, now that cannot be 0 because 0 is restricted for this curve. So I'm going to change this to 1, 0. Okay, so I'm going to change this to 1, 0 in order to be able to find that constant of integration, because x equals to 0 is restricted for the curve. So over here, replacing x by 1 would actually give me 1 plus 2 minus 1/3 plus k equals to 0. Then over here, this is 3 minus 1/3. This is an 8 over 3 plus k equals to 0. Then k is negative 8 over 3. So finally, we end up with f of x to be x plus 2 over x minus 1 over 3x cubed, of course, minus 8 over 3 as the antiderivative we are looking for. So this is the antiderivative of the function small f of x that passes through the point 1, 0. So here, just finding this antiderivative as a last example. So again, we look at this as, so we can always just leave the constant aside. So we look at this as negative 5 over x to the 7. So applying this rule, I'm going to rewrite that here again. 1 over x to the n dx is negative 1 over n minus 1 x to the n minus 1 plus k, and over here we have it in the form x to the n, which is 1 over n plus 1 times x to the n plus 1 plus k. I remind you that 1 over x to the 7, sorry, deleted that by mistake. So 1 over x to the 7 could still be used using this rule for n equals to negative 7, but however, do not forget to just bring back the expression in terms of positive exponents. So if I were to call this integral I, so I is, so I just keep the negative 5 and multiply by an antiderivative of 1 over x to the 7. So this rule for n equals to 7 would actually give me negative 1 over 6x to the 6 plus 3 times. Now this rule for n equals to, 2 here, because I have an x squared, that would give me 1/3 x cubed minus square root of x. Now square root of x, you could apply this rule for n equals to half, or we have already found it in our table of integrals. We already have it there as 2/3 x square root of x, of course, plus k. So simplifying our expression here would give me 5 over 6x to the 6 plus x cubed minus 2/3 x square root of x plus k. So that would be my antiderivative. Since over here I do not have a particular point given in the question, then my final integral would be in terms of my constant of integration. Now, before we wrap this up, I would just like to note that in order for you to check that you have integrated correctly, what you can do is take the integral or the answer you got for the integral and then find its derivative. Now, once you find the derivative of this expression, you have to go back to the expression you originally started with inside the integral. If you did not go back to the function you started with inside the integral, it means that you've done something wrong, whether in the derivative itself, in the process of checking, or in the process of integrating. Now, this was all regarding the introduction to antiderivatives. Now, in our following lesson, we're going to tackle some integration techniques for functions that are a little bit more complicated than just than the functions that you directly apply the integral rules to. Because over here we've just explored the rules for integrals or the table of integrals. We've seen these couple of examples where you'd be applying directly these rules. Now, it could be, and it's most likely to be more complicated than that. So in our next lesson, we're going to start by exploring some further integration techniques.